Bismillahirrahmanirrahim. Welcome to the channel. My name is Asim Amjad, and in this video lecture we still discussing the lecture number 10, that is related to elastic beam bending. The objective of this lecture are to locate the neutral axis for a cross section of a beam that is subjected to a pure bending, and finally we derive the moment curvature relationship. In the previous video we investigated the longitudinal strain EH in a beam in pure bending. Since longitudinal elements of a beam are subjected only to tension or compression, that we can use the stress strain curve for the material to determine the stresses from the strain. The stresses act over the entire cross section of the beam and vary in intensity that depend upon the shape of the stress strain diagram and the dimensions of the cross section. So let's start talking about the stresses, and let's say that our beam has this short type of T type of cross section, and we talked about the last time for this type of beam bending we are going to have compression about the neutral axis and we are going to have tension below the neutral axis, and that I have shown that here. The most of the stress-strain relationship encountered in engineering is the equation for a linearly elastic material, that is sigma is equal to E times epsilon. Please note that for most of the material in elastic range, that it is reasonable to assume that the tension and compression stress-strain curves are the same. So therefore Hooke's law applies the same for both tension and compression. In the previous video, we derived the strain curvature relationship, that is epsilon x is equal to minus y over rho, that's also equal to minus kappa y. Substituting this EH into this equation, then you come up with this equation, and after rearranging this term, you finally come up with this equation, that is minus E times kappa times rho. So for linear elastic materials, stress is also proportional to curvature and varies linearly with distance y from the neutral axis. In order to make practical of this equation, we must locate the origin of coordinates so that we can determine the distance y. In other words, we must locate the neutral axis of the cross section. So to obtain the neutral axis, we consider an element of area dA in the cross section. The element is located at distance y from the neutral axis, and therefore the stress sigma x acting on the element is given above. So the force acting on the element is equal to sigma x times dA and is compressive when y is positive, because there is no resultant force acting on the cross section. So the integral of sigma x dA over the area A of the entire cross section must vanish. So the equation becomes integral of A modulus of elasticity E times K times y dA is equal to 0. Simply substitute this sigma x value into this equation, then you come up with this equation. And because the curvature K and modulus of elasticity E are non-zero constants at any given cross section of a bent beam, they are not involved in the integration over the cross section area. So therefore we drop them from the equation and we obtain integral of A y times dA is equal to 0. This equation is also known as the first moment of area with respect to z axis. In other words, the z-axis must pass through the centroid of the cross section. Since the z-axis is also the neutral axis, so we have arrived at the following important conclusion, that the neutral axis passes through the centroid of the cross section area when the material follows the Hooke's law, and there is no axial force acting on the cross section. So this observation made it relatively simple to determine the position of the neutral axis. Okay, now let's move to the second objective of this lecture, that is moment curvature relationship. The moment resultant of the normal stresses sigma x acting over the cross section is equal to the bending moment m. So the element of force sigma x dA is basically acting on the element of area dA, and it is in the positive direction of the x-axis when sigma x is positive, and it is in the negative direction when sigma x is negative. As the element dA is located above the neutral axis, so a positive stress sigma x is acting that element, and it produces an element of moment that is equal to sigma x times y times dA. So taking positive direction of counterclockwise, summation of moment at z axis is equal to 0. So dm, this moment dm plus sigma x y times dA is equal to 0, and rearranging this equation would become dm is equal to minus sigma x times y times dA is equal to 0. We also know that sigma x is equal to minus E times kappa times y. So the integral of all such element moment over the entire cross section area A would equal to the bending moment, that is m is equal to minus integral of A sigma xy dA. Substituting this value into this equation, then moment would become integral of A E times kappa times y square dA. This negative would be cancelled out this negative term. This equation relates the curvature of the beam to the bending moment m, and the integral is the moment of inertia of the cross section area with respect to the z-axis, that is with respect to the neutral axis. So after rearranging this equation in terms of bending moment, the moment curvature relationship would become k is equal to 1 over rho is equal to m over ei. So this equation is known as the moment curvature relationship, and it shows that the curvature is directly proportional to the bending moment m and inversely proportional to the quantity ei. This ei quantity is called fracture rigidity. It's basically the resistance of the beam to the bending for a given curvature. So as if it is larger the fracture rigidity, so the smaller the curvature for the given bending moment. So this concludes our lecture, and next time we will discuss about fracture formula.